Great. Well, it's my pleasure to introduce Dr. Laura Larocca, who is our UTIG speaker today. Dr. Larocca holds the prestigious NOAA Climate and Global Change Fellowship, which she's currently deploying at Northern Arizona University in their School of Earth and Sustainability. And her work focuses on characterizing Arctic climate and glacial fluctuations over decadal to millennial timescales. And she really uses an impressive array of techniques to do this, including paleolimnology, remote sensing, geospatial analysis, and as I learned yesterday, also military flight campaigns from the 1920s, which is really interesting. So today she'll be providing an overview of her work on the Holocene history of Arctic glaciers, insights into past climate, and the future evolution of Earth's cryosphere. So take it away, Laura.
Thanks for that introduction, and hello to everyone. Thanks so much for having me today. Yeah, so today I'm going to talk about the long-term history of Arctic glaciers and the implications that history has for our understanding of Holocene climate and the future evolution of the Arctic cryosphere. So to begin, I thought I'd just briefly introduce myself and what my broad research program looks like. So I'm interested in contemporary change in Earth's climate and cryosphere, and also in the reconstruction of past climate and environmental change. So my work draws on approaches and tools from several fields like paleolimnology, remote sensing, and geospatial science. And I really use this cross-disciplinary approach to investigate recent historical and also longer-term climate and glacier fluctuations on timescales of decades to millennia. And I've also done this in focused regions like in South Greenland and also in the wider Arctic. I've also led remote fieldwork expeditions to Greenland. So in this background picture here, I'm standing with my colleague, Melissa Chipman, and we're standing at a field site in South Greenland and holding up a sediment core from a glacial lake that we collected. So in this talk, I'm going to share two recent projects. The first uses lake sediment archives and geospatial methods to reconstruct Holocene glacier status and climate in southern Greenland. And the second synthesizes all published Holocene glacier records from lake archives across the entire Arctic. And before sort of jumping into the details, I'll describe the significance, motivations, and key questions that really drove this work. And lastly, I'll briefly talk about what I'm working on currently in my postdoc and what I envision for my future research, and also some outstanding questions that really excite me. So I also wanted to note here that the work I'll describe today is focused on glaciers and ice caps that terminate on land and that are distinct from Earth's two remaining ice sheets, the Greenland and Antarctic ice sheets. Okay, so I just wanted to start out by showing the first figure from the summary for policymakers of the sixth assessment report of the IPCC. And it shows the history of global temperature change and highlights the utility of paleoclimate data in informing our understanding of recent warming by placing it into a longer term context. And in doing that, this figure illustrates the unprecedented nature of recent warming really well and shows that global surface temperature of the most recent decade, shown in this pink dot, was likely warmer than any multi-century period during the Holocene, and that temperatures are now rising to levels unseen since the last interglacial, which was over 125,000 years ago. So information from paleoclimate archives and model simulations also tell us that during past warm periods, really dramatic environmental change took place, including large changes to Earth's cryosphere. So for example, a recent review by Dutton et al. Really drives home the point that during past interglacials, small increases in global mean temperature and just a few degrees of polar warming resulted in at least 6 meters of global sea level rise. And this was primarily due to large reductions in glacier extent and ice sheet extent. Similarly, during the early to middle Holocene, relatively modest warming caused retreat of glaciers and the Greenland ice sheet, the northward migration of various plants and animals, permafrost thaw, and also decreased perennial sea ice cover. So over the past several decades, we've really begun to see the dramatic effects of recent warming on the Earth's cryosphere. And today, global mean sea level is rising and accelerating, mainly due to contributions from both glaciers and ice sheets. And this figure here from Zemp et al. Shows just the global glacier contribution from the 1960s to present. So in addition to raising sea level, the continued loss of glaciers is expected to have many local scale impacts. So for example, changes to water flow and sediment loads in glacially fed meltwater streams has the potential to impact water quality and downstream ecosystems. Glacier melt will also have impacts on numerous areas related to energy, tourism, and natural hazards, and is expected to have socioeconomic and cultural implications for often overlooked communities that have lived on and stewarded their homelands for millennia. So despite these global and local scale consequences, glacier mass change stands out as one of the least constrained elements of the global water cycle. And it was actually identified as a critical research gap in the recent special report of the IPCC. And as you can see in this figure, over the recent past, global glacier mass loss was as great as that from the Greenland ice sheet. However, the rate of ice loss from glaciers has a much larger uncertainty. Even though it's virtually certain that glaciers will lose considerable mass by 2100, there are even greater uncertainties in their evolution and future end-of-century projections. And this is in part due to limited observations, especially prior to the satellite era. So only a small fraction of the Earth's 200,000 glaciers have any in situ mass balance measurements. And the red dots here on this map show the small number of glaciers worldwide that have more than 30 years of ongoing measurements. So the lack of observational records is especially apparent in remote Arctic regions. So for example, Greenland is an island about 3 times the size of Texas, and it hosts almost 13% of the world's glaciers and ice caps by area. Yet there's only one glacier there with multi-decadal mass balance measurements, and they begin around 1995. So similarly, knowledge of glacier fluctuations prior to modern historical time is still relatively sparse. This figure is from a 2015 review, which synthesized all global records of glacier variations based on multiple proxies over the Holocene. And the Holocene encompasses the last 12,000 years or so of Earth's history. So these limitations in observational records and in longer term records really hinder our understanding of glacier response to external forcing, particularly to sustained warming. And it also leaves us with uncertainties and projections of sea level rise and coastal flood risk over coming decades, and in the lifespan of water supplies coming from mountain glaciers. So a recent high-profile study here by Khan et al., I think provides a nice example of how longer-term glacier observations can help to constrain future projections. So in this study, they used a set of historical photos, and the study estimated ice loss from Greenland's 3 largest outlet glaciers, Jakobshavn, Kangerlussuaq, and Helheim, and they did this between 1880 and 2012. So the study estimated that the amount of ice lost during this 130-year period was comparable to the projected loss by 2100 under the worst case scenario. However, in the future scenario, temperature change is estimated to be about 4 times larger than that which has taken place since 1880. And so this strongly suggests that future projections of mass loss from these 3 glaciers are likely severely underestimated and could far exceed that worst case scenario set out by the IPCC. So the other major theme that drives my work is our understanding of Holocene climate. And although it's been relatively widely studied, many key questions remain. So in the Arctic, previous syntheses of multi-proxy data, such as the study shown here by Kaufman et al., suggest spatial and temporal asymmetries in temperature change over the Holocene, including in the pattern of peak Holocene warmth, which is often referred to as the Holocene thermal maximum. So to fully understand the mechanisms and processes that drive this heterogeneity in regional climate, we need a clearer and more detailed picture of Holocene temperature change. And these details will also help us to anticipate how the Arctic might change in a warming world. So because small mountain glaciers are exceptionally sensitive to modest climate change and predominantly to changes in melt season temperature, records of their past fluctuations are considered relatively straightforward qualitative proxies for summer temperature and have been widely used to expand our knowledge of past climate. So in the work I'll talk about today, I use 2 main archives of glacier change, which are bolded here, to understand how glaciers and by inference climate has fluctuated over the Holocene and the recent past. So the first approach involves the use of lacustrine sediments from glacial lakes, and glacial lake sediments are especially useful archives because they can record glacier change continuously over the entire Holocene. So the basic idea here is that sediment is deposited year after year in lakes, and that accumulated sediment serves as an archive of the local environment and of glacier history. So to infer change in glacier size over time, including their presence and absence on the landscape and also more subtle variations in their size, I look at the physical and geochemical properties of the lake sediments. So in general, a dominant input of inorganic, fine-grained silty clays and a blue-gray sediment color indicates the presence of an erosive glacier in the lake catchment. Whereas sediment that's more brown in color and higher in organic material indicates that the glacier was smaller than present or completely absent, which tells us that summers were warmer. So second, I take advantage of geomorphic evidence that records glacier extents larger than today and periods of cooler than present summers. So the photo on the left here is at a site in Greenland, and the white dashed line shows a terminal moraine, which is a massive glacial till deposited by a glacier, and it's often in the form of a long ridge and marks that glacier's past extended state. I also use trim lines, an example of which is shown here in the yellow dashed line. And these mark past glacier thicknesses and are usually visible due to changes in color to the rock or changes in vegetation on either side of a valley formed by a glacier. So together, I use this evidence to place constraints on past glacier extent and height to model past glacier surfaces and their mass balance parameters. Okay, so now I'll just jump into one of my recent studies, which looked at Holocene climate and glacier history in southern Greenland, which is a really climatically distinct and also understudied region within the northern North Atlantic. So in this work, I combined glacial lake sediment analysis and the modeling of past glacier parameters to determine the timing of past glacier fluctuations over the Holocene, as well as the corresponding summer temperature change required to cause those fluctuations. So like the broader Arctic, most of Greenland experienced warm summers in the early Holocene due to changes in Earth's orbit. However, peak warmth is thought to have varied geographically across Greenland and to have differed by thousands of years and by several degrees between locations. So for example, two well-known reviews had suggested that sites around the Labrador Sea and southern Greenland may have experienced a subdued or later period of maximum warmth relative to summer insolation forcing and to climate at sites farther north. However, this was based upon very sparse data. Previous work had also suggested that this pattern was likely due to the region's proximity to diminishing Pleistocene ice sheets, including the Laurentide ice sheet, which lingered well after peak insolation. So episodic meltwater discharge from retreating ice sheets in the early Holocene is thought to have influenced sea surface temperature and ocean currents and dynamics, including the strength of the Atlantic meridional overturning circulation. So in South Greenland in particular, the existing paleoclimate records from the region, which are shown here in these yellow squares, are actually inconsistent with one another and suggest that the Holocene thermal maximum took place as early as 9,000 years ago to as late as 6,000 to 3,000 years ago. So a main objective of this work was to test if South Greenland experienced a delayed and subdued Holocene thermal maximum by constraining the timing and magnitude of the warmest and coolest periods of the Holocene using lake sediment records of glacier activity. And this was also especially exciting work because in contrast with other regions of Greenland, no previous study had determined the Holocene history of glaciers in southernmost Greenland. So in the summer of 2018, we collected lake sediment cores from 3 glacial lakes between Kohortok and Cap Farvel, which is the southernmost point on Greenland. And our sites here are marked by these purple dots on the map. So I'm just zooming in here on one site, Alakarisok Lake, to give you an idea of what our field sites looked like. So on the left is a photo of the glacial lake, and on the right, I'm showing a satellite image which shows a bird's eye view of the lake and the surrounding area. So the lake's watershed is outlined in this cyan line, and the positions of the terminal moraines are shown by these dashed yellow lines. The image also shows the 4 mountain glaciers that are within the lake's watershed today, along with their elevation range. The 2 other lake sites that we visited also have small mountain glaciers within their watersheds today, and so their absence in the past would indicate warmer than present summers. So in the field, we used an EdgeTech acoustic sub-bottom profiling system to image the sediment and to select coring locations at each lake site. And the sonar data was a really handy field tool as it gave us an idea of the sediment package thickness and allowed us to find coring locations that avoided things like disturbed sediment, trapped gas, boulders, or steep slopes. And some of the sonar data we collected is shown for the 3 lakes on the top panel here. And the strong reflections mark boundaries between sediment with dissimilar characteristics. So back in the lab, I used a geotech core logger to distinguish minerogenic rich glacial sediments from organic rich non-glacial sediments. And to do this, I measured magnetic susceptibility, visible color reflectance, excuse me, and major element abundance using X-ray fluorescence spectroscopy. I also determined sediment organic matter content by loss on ignition. And I based our core chronologies on carbon-14 dating of aquatic macrofossils. And finally, to characterize the leading modes of variability in the measured geochemical and physical properties, I used principal component analysis. So here's the resulting data from the 3 lakes. Age is shown on the horizontal axis and moves towards the early Holocene here on the right. And I use the PCA1 scores to summarize changes in minerogenic input. And so the positive PCA scores here indicate sediments that are more minerogenic rich and indicative of larger glaciers and thus cooler summers. So most importantly here, our data show that Cubnerit and Alakari-Sauk lakes received meltwater input from local glaciers from the onset of lacustrine sedimentation in the early Holocene until around 7,000 years ago. And this implies relatively cool summer conditions at these sites during the early Holocene. At around 7,000 years ago, the 2 lake records show a nearly synchronous shift to organic sedimentation, which indicates that the local glaciers in their catchments completely melted away and that summer temperatures were warmer than present by this time. And our results here suggest that the Holocene thermal maximum took place in South Greenland between 7 and 5.5 thousand years ago. And so our early and our middle Holocene climate inferences provide strong support for those review studies that synthesized proxy climate data from the Arctic and had suggested, based upon very sparse data from the region, that southern Greenland experienced a relatively cool early Holocene and a delayed thermal maximum. And this also supports the notion that the waning Laurentide ice sheet had profound effects on the North Atlantic region during the early Holocene. So as summer temperatures cooled in the late Holocene, our records show that sustained glacier regrowth began around 3,000 years ago with glaciers in the southernmost catchment, which at present receive the most precipitation. And in the other 2 catchments, which host smaller glaciers in a drier environment, regrowth began at 1.3 and 1.2 thousand years ago. At the very top of our cores, we see increased minerogenic input at our study sites, and this suggests cooling and glacier growth in the Little Ice Age, which is a recent cool period when most of Greenland's glaciers reach their maximum Holocene extents. So just to recap here, from our lake records, we've now constrained the timing of Holocene glacier and climate fluctuations. And now I'm going to describe how I provided quantitative estimates of the magnitude of summer temperature change during the warmest and coolest intervals of the Holocene. So I'll just start here by summarizing the methodology that I used to do this. So the equilibrium line altitude, which I'll refer to as the ELA, marks the line or zone on a glacier where accumulation or mass gain is balanced by ablation or mass loss, usually over a 1-year period. And the position of the equilibrium line altitude is largely dependent on 2 main factors: snow accumulation and melt season temperature. So for example, warm summers and low accumulation will cause the ELA to rise and the glacier geometry to shrink towards a new equilibrium state. Alternatively, cool summers and more accumulation will act to lower the glacier ELA, and the glacier will grow towards a new equilibrium state. And the summer temperature change responsible for a shift in the elevation of the glacier ELA can be approximated using a local atmospheric lapse rate. And this in turn yields quantitative constraints on Holocene temperature. I also wanted to mention that I define that shift in ELA relative to present. So in other words, I compare the ELA of the past glacier with the present ELA, which I estimate using glacier snow lines. And the snow line is just the line in which white snow meets glacial ice, and it can be used over several years as a proxy for the position of the ELA on modern day glaciers. I also use the concept of the critical ELA threshold, which is the ELA threshold tied to glacier birth and death. And this is represented by the highest elevation at which ice accumulates. So when the ELA rises above this threshold, the glacier will no longer have an accumulation zone and is considered doomed to melt away. Alternatively, when the glacier dips below this threshold, ice begins to accumulate and a glacier is essentially born. So these figures summarize the glacier ELA modeling results for each of our sites, but to make things a little bit easier to see, I'll just zoom in here on one site. So here the present day glacier surfaces and extents are shown here in the white polygons, and the mean snowline elevations are denoted by these blue lines, and the highest ice elevations are shown in these purple circles. So beginning here with the Holocene thermal maximum case, since the lake sediment records indicate that glaciers completely melted away during the middle Holocene, we know that glacier ELAs must have risen above that critical threshold. And so I treat the highest elevation on the present glaciers as the minimum Holocene thermal maximum ELA. So based on the average ELA rise between the present snow lines and the glacier's highest elevations, I find that these sites were at least 1.2 to 1.8 degrees Celsius warmer than present during the Holocene thermal maximum, so about by 7,000 years ago. And this information also implies that summer temperatures didn't rise well beyond that during the early Holocene, when our sediment records show evidence of glacier presence. So I then estimated the magnitude of Little Ice Age cooling by comparing present snow lines with modeled Little Ice Age ELAs. So the glacier's expanded state and surface during the Little Ice Age is shown in the gray polygon here. And again, this larger extent is constrained by glacial moraines and trim lines. And so the Little Ice Age ELAs, which is shown here in this pink line, were modeled using two ArcGIS toolboxes. The first is called GLAIR, and GLAIR generates ice thickness from bed topography along user-defined flow lines, and it's based on an iterative solution to the perfect plasticity assumption for ice rheology. And the tool uses interpolation methods to generate that three-dimensional surface of the past glacier. So I then use this modeled surface output from GLAIR in a second toolbox developed for the automated calculation of glacier ELAs to get at this Little Ice Age ELA. And so based on the average ELA lowering from our present snow lines to the Little Ice Age ELAs, I found that summer temperatures were at least 0.4 to 0.9 degrees Celsius cooler than present at our sites during the Little Ice Age. So finally, I compared our glacial lake records from South Greenland with all other continuous lake records of glacier change across Greenland, and I organized them here from north to south. And age is shown here in thousands of years before present on the x-axis. So the gray bars show when glaciers were interpreted to have melted away completely or were smaller than present. And the blue bars indicate when glacier ice was present in the lake catchments. So although these records are still few in number, they are beginning to reveal some broad patterns, and they show that most glaciers fluctuated significantly through the Holocene. In addition, these records suggest that the timing of local glacier disappearance or reduction in extent is broadly associated with latitude, with glaciers in southern Greenland becoming smaller or absent later in the Holocene than those in the north. And this pattern is also consistent with that north to south trend in the timing of Holocene warmth that was tentatively observed in that review of temperature sensitive proxy records by Briner et al. That I had showed previously. Okay, so now I'm going to jump into a second recent study, and in this work, I synthesized all published records of Holocene glacier and ice cap fluctuations from lake archives across the entire Arctic. And these records are very similar to those I presented in southern Greenland and use very similar methodology to distinguish glacial from non-glacial sediments and to document glacier change and glacier size change over time. So in the review, we included 66 records from 7 Arctic regions, and 4 of which are from my work in South and Southwest Greenland. So the major goal of this work was to use this very specific archive type to assess Holocene climate change in the Arctic, and specifically to evaluate the timing of summer warmth and cooling in each region and Arctic-wide. And this was the first geographically broad synthesis to solely focus on lake-based glacier reconstructions. So to represent the evidence from each of the lake records, we used a binary approach and defined glacier status in 100-year intervals from 12,000 years ago, where 0 equals glacially influenced sediment and glacier presence, and 1 equals sediment indicative of a glacier smaller than present or completely absent. And again, we interpret a smaller than present glacier or an absent glacier as indicative of summers warmer than present. So in the interest of time here, I'm just showing the results from the full Arctic compilation. So time is moving from the early Holocene on the left towards present on the right. And on the top panel, I'm showing the percent of glaciers or ice caps smaller than present or absent over time. So the line shows the percent in 100-year bins, and the bars show the 500-year bin means. The open dots here show the timing of glacier regrowth in the middle to late Holocene for each study versus the glacier's highest elevation. The line on the bottom panel here shows the number of records over time, and the bars show the slope between these 500-year bins above. So Arctic-wide, I found that the majority of studied glaciers were small or absent by around 10,000 years ago. And this suggests that summer air temperatures were warm around much of the Arctic quite early in the Holocene. So using that critical ELA threshold concept that I described previously, I also estimated the summer temperature rise needed to elevate the glacier ELAs above their modern ice surfaces. And this gives us an average magnitude of Arctic-wide summer warming of roughly 2 degrees Celsius above present between 10 and 8,000 years ago. And this was the time when most glaciers first became smaller or melted away. And I think this is an especially important point because in comparison, future projections of Arctic temperature change exceed 2 degrees Celsius of warming in most locations, suggesting the eventual loss of most of the Arctic small glaciers. I also found that more than 90% of Arctic glaciers were smaller than present or absent in the middle Holocene. And we conclude that this likely reflects the more spatially ubiquitous and consistent summer warmth during this period than in the early Holocene. So following this interval of widespread warmth, our compilation shows that glaciers across the Arctic began to regrow and that summers began to cool by around 6,000 years ago. And the records also suggest 2 periods of enhanced glacier growth and perhaps higher rates of cooling in the mid to late Holocene. And these periods are indicated by the larger change in slope between the 500-year bin means and are highlighted here in this darker blue. Our results also suggest a weak relationship between the timing of glacier growth and the maximum glacier elevation. And this reflects that topography probably had some influence on the pattern of glacier regrowth, and that very broadly, as summer temperatures declined, ELAs lowered to intersect the local landscape, and glaciers regrew on the highest peaks first. So finally, I'll just summarize what I think are the 2 most important takeaways from these studies. In the first study, I found that South Greenland's glaciers survived the early Holocene and melted away later relative to glaciers in the north, providing really strong evidence that supports the notion of a delayed Holocene thermal maximum there. So importantly, this study also suggests the idea that changes in large-scale overturning circulation in the early Holocene caused major climate impacts in this region, and thus it has implications for predicting how discharge from a shrinking Greenland ice sheet might affect future North Atlantic climate. Second, the circumpolar compilation of lake-based records implies that most of the Arctic's small glaciers melted away completely in response to summer temperatures that were only moderately warmer than today. And future projections of temperature change in the Arctic exceed that value in many locations, even in the best case low emission scenarios, suggesting that most of the Arctic small glaciers will melt away entirely. Okay, so I'll just use the rest of the time here to talk about my plans for research in the near and longer term. So my current work has focused on the question of when, specifically when will the Arctic's 40,000 plus land terminating glaciers and ice caps lose their accumulation areas and essentially be doomed to melt away? And I think this is a really important question, as predictions of glacier loss will be relevant for local scale impact studies and adaptation and mitigation planning for changes in hydrology and water resources. So the currently available large-scale studies that project glacier mass change most often aim to estimate glacier volume loss and their contribution to sea level rise by the end of the century. However, these projections generally don't resolve sub-regional trends in ice loss over time, nor do they predict when individual glaciers will melt away. So in my postdoc work, I'm taking a different approach, and instead I'm working to model when individual glaciers and ice caps, when their ELAs crossed and will cross those topographic thresholds which equate to glacier birth and death. And I'm doing this from the middle Holocene into the future to 2100 CE. So the work will give insight into the lifespans of glaciers, the regional patterns in climate and glacier response in the middle and late Holocene, and will also predict which glaciers are most at risk of melting away first under different future scenarios. So here I'm showing a schematic of the project methodology, and time is on the x-axis here and moves from the middle Holocene on the left into the future on the right. On the y-axis here, I'm showing the ELA change, which is driven by change in summer temperature. So the blue line represents ELA change through the Holocene, and glacier birth occurs when the ELA dips below that highest topography at which ice accumulates. And the red, yellow, and green lines represent ELA change into the future under 3 warming scenarios. And glacier death occurs when the ELA rises above that highest topography at which ice accumulates, leaving the glacier with no accumulation zone. And this work has really only recently become feasible given some newly developed tools, data sets, and syntheses, which I'll briefly mention in the next few slides. So to model glacier ELA change through the Holocene, I'm using a new paleoclimate data assimilation product by Michael Erb, which combines climate model simulations with temperature sensitive proxy records from the temperature 12K database to reconstruct temperature evolution over the Holocene. And the database of Holocene temperature records was developed at Northern Arizona University by Daryl Kaufman and colleagues. I'm also making use of my circumpolar synthesis of Holocene lake-based glacier records. And specifically, I will compare my modeled simulations of glacier birth with the lake-based geologic constraints. To estimate present glacier equilibrium line altitudes, I'm using recent methodology presented by Rassner et al., which maps snow cover and snow line elevation on glaciers using Landsat imagery and an automatically selected glacier-specific reflectance threshold to separate snow from ice. So James Lee is a collaborator on this work, and James is working to implement this methodology into Google Earth Engine, which will greatly reduce processing times. So here I'm just showing a graphical user interface created and shared by James, which shows mapped snow cover and ice on an example glacier in East Greenland. So finally, to model glacier ELAs into the future, I'm using climate model simulations of summer temperature from phase 6 of the coupled model intercomparison project. And I plan to use projections forced by 3 mid-range emission scenarios. So my longer term research will continue to draw on tools and approaches from multiple disciplines to advance understanding of cryosphere evolution in response to climate change on decadal to millennial timescales. And I think there's really great potential to provide a more complete view of past, present, and future climate and glacier change across the Arctic by bridging these traditional subfields. So this will involve integrating paleoclimate and historical data with remotely sensed observational data sets, along with climate and glaciological modeling. So I'll focus on questions that really aim to better near-term regional scale predictions of glacier loss by first working to improve understanding of regional climate dynamics and climate-glacier relationships. Second, by expanding data sets of glacier fluctuations, both in recent and historical time, and also their longer-term Holocene histories. And third, by better quantifying the state of present-day glaciers. So a few specific topics and outstanding questions that excite me include the historical response of Greenland's outlet glaciers. So although glacier change across Greenland has followed a similar trend, there are regional differences in their fluctuations through the 20th and 21st century. And questions remain about whether this is due to regional differences in climate and glacier sensitivity, or likely some combination of both. Second, there are still large spatial data gaps in records of Holocene glacier fluctuations. So for example, my review identified that there are only 5 or 6 lake records from Alaska and the Canadian Arctic. And also in northern Greenland, there's mounting evidence of strong and early Holocene warmth there, but the very few glacial lake records indicate that glaciers may have survived that warmth. And third, because most glaciers are out of balance with recent warming, they are committed to some continued mass loss in response to past emissions. However, quantitative estimates of the scale of this disequilibrium are still sparse, especially for Greenland's peripheral glaciers. And as far as broader impacts go, the research will have implications for better predicting rates of sea level rise, for local hydrological change and water resources, and for adaptation and mitigation planning for Arctic communities. And along with research, I very much value student involvement, including opportunities for mentorship and training in independent research projects and also in field experiences. And I also really value community collaboration and service, including actively working to build an inclusive geoscience community and also working to increase public knowledge of geoscience career paths and also of the impacts of climate change. So I'd like to just acknowledge all my colleagues, co-authors, and funding sources that helped to make all this work possible, and the people of Greenland who welcomed us to work on their land. So thank you, and with that, I'll welcome any questions.
Wonderful. Thanks very much, Laura, and I'll do some Zoom style applause for a great talk. So if folks have questions, we have time for a robust Q&A, and people can either put things directly in the chat or raise your hand, and I'll call on you to unmute yourself. But while people are coming up with their questions, I'll ask one that Duncan Young submitted. He had to hop off early, but he had a question about the sediment cores from glacial lakes, and he's asking, can you distinguish sediments from former subglacial lakes from superglacial lakes?
So lakes like with on the ice sheet?
Maybe one of our cryosphere people on the call can try to shed more light on that. Yeah, so he's asking, I guess he's asking whether you can distinguish sediments from different glacially related lake types. Yeah.
Yeah, that's an interesting question. So one of the things that we had planned to do in southern Greenland that we actually couldn't end up doing because of some bad weather was visit a lake where within the watershed there were lots of different glaciers that sat on different bedrock types. So one of the questions that we were interested in looking at was whether we could see the signal of changes in different glaciers based on the geochemical data that we collected. So I think that's still an open question.
Great, so I see Patrick just raised his hand. Patrick, go ahead.
Yeah, hi Laura, thanks for an excellent presentation. I was wondering whether if you doing the reconstructions around the Greenland margins, whether the patterns and the timings tell you something about the reorganization of the atmosphere throughout the Holocene period that may shed light on basically a bit the causes of what led to the cooling after the rewarming, and how that is spatially maybe yeah, just the atmosphere, how it reorganizes, for example, with change in topography. And maybe related to that, could you take advantage of isochrone layers over Greenland? You don't have lakes, right? And so you can't do any reconstruction, but you have now isochrone layers in the Greenland ice sheet that also give you a history of the Holocene, perhaps. And would that be a useful complementary information for them?
Yeah, I definitely think it's useful information. And I think lake records from around the Greenland ice sheet have been really important because they give us a sense of how temperature has changed over the Holocene, and we can compare those records with how the Greenland ice sheet margin has changed. So I think records even non-glacial records that look at temperature change over the Holocene can really give us some important insight into how the Greenland ice sheet has reacted to temperatures warmer than present in the recent past. So I think it's, yeah, definitely complementary fields, and information from these lake records are really important in understanding the atmospheric conditions and the reaction of the Greenland ice sheet over the Holocene.
I actually had a big picture question about the sort of ELA behavior that was central to a lot of the analysis. So you'd mentioned that one of the current model, or like one of the limitations of the current model of how ELA responds to climate, is that it only considers temperature and it assumes that there's no change in precipitation, which I imagine might be pretty important for individual glaciers and even at the regional scale. And so I'm curious, has there been any attempt to assess how large of a bias that might create for some of the specific glaciers that you've been looking at? And what are some of the challenges to trying to incorporate precipitation influences into that model of how the ELA responds to climate? Because it seems like, especially going into the future, we know there are going to be large precipitation variations that could play a large part.
Yeah, that's definitely, I think, one of the big limitations to the method that I used. We tried to deal with that limitation a little bit by reporting our temperature estimates as minimum constraints. So if precipitation was higher, let's say when it was warmer in the middle Holocene, that would act to counteract that ELA rise. And so reporting these estimates as minimum constraints helps with that limitation. But yeah, it's definitely something that I'm thinking about in my future work. But temperature and precipitation usually move in the same direction. So when it's warmer, it's usually wetter, but in the future, projections suggest that we'll actually get more rain instead of snow, and that will have really different effects on glacier mass balance, especially on the reflectance of the ice. So yeah, it's definitely a big limitation to this method.
Yeah, and it seems like, especially at a regional scale, sort of circulation related changes in the distribution of precipitation could also play a role. So I was thinking about how you would disprove the sort of alternate hypothesis that the difference between the southern Greenland glaciers and the northern Greenland glaciers is more precipitation than temperature related. Did you all explicitly look at that alternative hypothesis and determine a way of sort of eliminating it?
Yeah, it's still unclear, I would say, but I will say that it takes a really large increase in precipitation to counteract warming. So studies have suggested it takes about a 30 to 40% increase in snow accumulation to counteract about 1 degree Celsius of warming. So it would have to be a pretty big effect in the early and middle Holocene, but it's definitely a possibility and something that, yeah, I'd like to look into further.
Great. So I'll go back to Patrick because I think his question was related, and then to David.
Yeah, maybe sorry, I had my question, but very quickly related to that. So this ELA modeling, you do not include ice flow, right? So it's not like an Erlenmann's type glacier model where you might expect you have, a rapid, for steep topography, there might be a significant impact also of the glacier flow on its change in geometry and its flow beyond the ELA line. And is that just a secondary effect, or?
Yeah, it doesn't include glacier flow. So it's just the change in the equilibrium line altitude. Yeah, just a threshold based approach. Yeah.
David?
I had two questions. The first is ELA related, so I'll do that first. I noticed in one of your study areas, I'm not going to pronounce the name right, but the one that starts Alakari something, they're the number of small glaciers, and the snow line, which you were using as a proxy for the ELA, depending on shading, changed by if I was reading it right, by 100 meters. So, which isn't surprising, but it does introduce an element of uncertainty, or at least a correction perhaps for shading and orientation of the highest peaks. Is that? So I was wondering how that is figured into what's going on. And then the other is you sort, at least when I look at your images, you just turn off the glaciers and turn them on based on what you see in the lake core. And having spent a fair amount of time looking at how sediment, when you remove a dam, how long it takes sediment to actually get flushed out after the dam is gone, and it can take, a century. What about those lags? I mean, should there be some error bars on the timelines that I didn't see?
Yeah, I guess I'll answer your first question. Sorry, your second question first. So yes, it does take some time for a glacier to completely melt away after that ELA rises above the highest elevation. But with these records, we have limitations based on the dating of the sediment. So often the errors on the carbon-14 dates are larger than the time it would take for that to happen. So it often does look like an instantaneous change, but it does take, decades to centuries for that glacier to completely melt away. And then as far as the snow line measurements, those were actually done manually for our lake records here. So we did account for any shading. So if there was an image in the Landsat catalog that was cloudy or that had a lot of shading that prevented us from identifying the snow line confidently, we didn't use that image.
Okay, I was just seeing, due to shading though, that the snow line was at different elevations depending on whether it was shaded or not shaded.
I think shading can definitely, you mean like year to year variations?
Yeah, well, maybe I read your plot wrong, but the 3 or 4 small glaciers, the one that had the big face open to the west had the lowest elevation, and I think another one had the highest that looked more shaded, but I read it wrong.
Oh yeah, okay, yeah, shading can definitely cause a snow line on a glacier to be higher because it's more protected from the sun. But that probably wouldn't change year after year, and that would be incorporated into our mean snow line elevation.
Okay, thanks.
I have just one last question related to some of your future directions. So there's a lot of debate, or there's a lot of disagreement in future climate model projections of what the strength of polar amplification is going to be. There's a wide range in what models project, and I wonder what contribution your work can make to sort of constraining the expected strength of polar amplification in response to future climate change. Do you think your work suggests that it should be on the higher end of current model estimates, somewhere in the middle? Sort of what constraint does it provide for that?
I think probably to answer that question, I would probably need more information from more sites around Greenland. So right now, yeah, I guess if you look at the circumpolar compilation, we're seeing around 2 degrees Celsius of warming in the early Holocene, but that's sort of a minimum constraint. So I think, unfortunately, it doesn't give us much information on the expected amplified warming in the Arctic. I think we would definitely need some more information from paleo records to answer that question.
Great, well, we're just past 11:30, so I think it's time to sign off. But thank you again for a really fascinating talk, and we look forward to seeing more of your work in the future.
Thank you. Thank you all.